The next lecture is entitled Fracture Toughness of a 9 CR ODS steel determined on tube specimens, and it's presented by Rais. Okay, perfect. Thank you very much.
I try to don't use the microphone too. Everybody can hear me?
I can hear you.
No, but I will use it. I will use it. So, hello everybody. I'm happy to be with you today. So I will present you my PhD research works on fracture toughness of ODS steels fuel claddings. So the fast neutron reactors or fourth generation nuclear reactors offer better efficiency in the use of uranium and reduce of radioactive wastes compared to the actual reactors. But these improvements induce a more severe service conditions in terms of thermomechanical stresses, especially for the fuel claddings. The tubes arranged in hexagon here. So the oxide dispersion strengthened steels or ODS steels are a good candidate for the fuel cladding of these reactors. It's thanks of their excellent resistance to swelling under radiation and their good mechanical and creep resistance at high temperature. But generally, increase of mechanical resistance means a decrease of ductility. So it is important to assess the toughness of these materials during their development. The fuel claddings in French reactors are a 10.7 millimeter outer diameter and the half millimeter thickness tubes. And its final geometry is obtained by cold rolling. This final step of shaping induces some microstructural modifications, so modify the mechanical properties of this material. So it is necessary to assess the toughness of this material in their final geometry. However, because of their small size, we can't sample standard specimens from these tubes. So the principal objective of my thesis is to develop an experimental procedure to assess the fracture toughness of tin wall tubes or of fuel claddings. To reach this objective, some tests are proposed in literature to assess the fracture toughness of specimens extracted from tubes. The PLT test for pin loading tension test, here in the red border, is often used in nuclear community and will be our reference test. So this presentation will follow these outlines. I will talk about determination of certain factors, geometric factors needed to analyze the PLT test. Then the crack length determination using the in-loading compliance technique. Then I will present you the experimental application of this experimental procedure to a 9 chromium ODS steel tube before concluding. First, just a little reminder of the determination of fracture toughness following a nonlinear fracture mechanics as given by the ASTM E1820 standard. To assess the toughness of materials with a certain ductility and presenting a stable crack propagation, we determine the J integral given by Rais and establish the resistance curve, which is the plot of this J integral as a function of the crack extension. The J integral is the addition of two terms, an elastic one and the plastic one. For the elastic J, this part depends on the stress intensity factor that depends on this geometric function noted F, which is given by standards for normalized specimen, but has to be defined for our PLT specimens. For the plastic J, it depends on this plastic factor noted eta PL. Now, this plastic factor, like for F, is geometry dependent and has to be defined for our PLT test. PLT specimen, sorry. So, because our material is precious, especially when irradiated, we use the single specimen method given by ASTM standard. For this, we apply some unloadings during the test, and from the elastic compliance of these unloadings, we determine the crack length. This crack length will allow us to determine the crack extension and calculate the plastic J using this incremental equation for a propagating crack. To determine these factors, we performed some finite element calculations, and thanks to its geometric symmetries, only a quarter of the fixture is meshed, and a contact with friction is introduced between the inner surface of the specimen in blue here and the outer surface of the mandrel in green. So please, if you can play, there are just a little video of this simulation. So if you can play it, please. So we apply some loads during the test. First, let's start with the F function, the geometric function F. So we perform some elastic mechanical finite element calculations, then calculate the J integral using G theta function. It's an implemented function in Castem, the software that I use in my study. So the J integral calculated is purely elastic because we use an elastic mechanical model, and knowing the other parameters, we plot the stress intensity factor as a function of this ratio, and the slope of this curve is our geometric function. So we repeat the exercise for different normalized crack size, A divided by W, to have the evolution of the geometric function for these different crack lengths. Now, the eta factor or the plastic factor. So for this, we perform some elastoplastic mechanical finite element calculations, and determine the J integral, which is a total integral. But knowing the F function, we deduce the elastic J and determine the plastic J, which is the total J minus the elastic J. So the evolution of this plastic J as a function of the plastic area under the load CMOD curve is linear, and its slope is our eta factor multiplied by a constant that we know. As for F, we repeat the exercise for different normalized crack lengths to have the evolution of this eta factor. Now, let's talk about the determination of the crack length. During some elastic finite element calculations for example, for a given crack length, we highlighted some phenomena that wasn't known before. These phenomena are the inflection of the curve at the beginning of the loading before being linear. So the phenomena responsible of this inflection are progressive contact and bending through the thickness. So the effect of this phenomena are the decrease of the compliance before reaching a minimum value, and that is this minimum value that we attribute at every crack length that we simulate. So we do this for different crack lengths to have the evolution of the compliance as function of the normalized crack length. And as we can see, the numerically defined C function is in accordance with the experimental results, the blue point. After that, we introduce this factor U, which is just a normalization of the compliance by the Young modulus of the material and the specimen thickness, and establish this equation permitting us to determine the crack length. So now we pass to the experimental application of this procedure. For this, we performed some tests on different specimens sampled on a nicromium ODS steel tube. The different crack lengths tested are referenced in this table. The loading program, consists of cycles of load, hold, unload, and reload every 30 micrometers of CMOD. And the CMOD is measured by an extensometer, as you can see in this picture. First, we observed during our experimental campaign that we have a crack initiation that occurs before reaching this minimum compliance. So this obliged us to use some optical measurements that we call a direct method to have the crack extension before reaching this minimum compliance. Beyond, we use our unloading compliance method or indirect method presented before to determine our crack extensions. To validate this indirect method, we compared the optically measured crack extensions to those determined or estimated from unloading compliances. So as we can see on this curve, which is the crack extension function of the CMOD, that the indirectly estimated crack extensions and the directly measured crack extensions follow the same evolution. And if we plot the unloading compliance estimated crack extensions as a function of the optically measured ones, we can see that the points are around this line, which is the one slope line. So we have a good estimation of our crack extension with the average scatter about 0.2 millimeter. Now, when plotting the raw resistance curves as obtained experimentally, we can see that we have a good reproducibility of our results with a very low scatter. So by fitting these curves by a power law as recommended by the ASTM standard, we can determine J 0.2, for example, of 40 to 55 kilojoule per square meter for this ODS steel tube. So to conclude, we developed an experimental procedure to assess the fracture toughness of ODS fuel claddings, following the ASTM 1820 for CT specimens. And this procedure can be applied to thin wall tubes. And using the unloading compliances, we can have a good estimation of our crack lengths with a certain scatter. So thank you for your attention.
Thank you for your talk. Any questions or comments?
Hi, thank you for your talk. When you compare the crack length or crack size in your indirect method with the direct method, in the direct method, what you are measuring is in the external surface, right? And the crack front is not completely flat, right? Yeah.
Yes, but there are not a big difference between the.
Okay. Okay.
So
And you assume that there is no difference during the whole propagation, right? Because maybe in the beginning you have a bit more difference.
here it's yes, there are a little different, but
Okay.
I don't consider,
Okay.
and that's why I have this scatter between the.
Okay. Good. Okay, thank you.
Okay. Here.
To ask a question, I just want to make a remark that about 25 years ago, we did a similar work on a different cylinder, small cylinder, completely different method, which I think is much simpler. I'll give you the reference later.
Okay, thank you.
Other question? Okay.
Thanks for your talk, of course. My question is, you used zircaloy as your material for the claddings in these, correct?
It's an ODS steel. It's an oxide dispersion strengthened steel.
Okay, good. So then it's okay. If it's not zircaloy, I don't have the question.
But it could be used for zircaloys.
Oh, zircaloy is on the way out. That's the issue. I was thinking of maybe extending to APMT or those materials that are more transport fuel. So
more ductile than this ODS
Questo
steel.
adesso.
So this phenomena doesn't happen before the crack initiation doesn't occur before our minimum compliance. So we can directly apply the indirect method. So that's the advantage on zircon alloy if we apply this experimental method.
Okay, thank you very much again. The last